so today we're going to be looking at doing different little demos on sound and resonance. And here we have our first table set up, and we have 6 pendulums, some that are matched meaning they have the same length. So this one and this one are matched, and here's another 2 that are matched, have the same length. And then this one doesn't have a match here. This is a very short one, and this one's a little bit longer, okay? And so you are supposed to think about what can you say about their periods of swing. So will these have period, meaning the time it takes to swing back and forth? Will they all have the same period, or what can you say about that? And then if you know that, what can you say about their frequencies? All right, then number 2 says, find an eye screw that has a matching length and set it swinging. So, and carefully watch what happens to the other pendulums. All right, so I am going to, well, let me do this one. I'm going to set this one going, okay? And we're going to watch what happens to the other ones. All right. So they all, so as this starts to swing, it is on hooked to this other arm that will start to swing because this is starting to make it swing. And so all of them feel kind of the push, almost like someone's pushing you on a swing. And what do you notice? Did you notice that they all moved a little bit, but this one set this one in motion. In fact, this one is now moving mostly, and this one has slowed. And as this one starts to move, it is now starting to make this one pick up again. All right, but you can see the ones that are matched definitely have influence on each other the most. The other ones are just a little bit moving, but they are swinging in time. And that is because they can resonate with each other. They have a matched frequency. So one is pushing at just the right time, and it wants to, because of its length, be able to swing with that, okay? All right, so we did that, and then you're supposed to answer what happens to the amplitude of the swing, etc. And then what happens, and then it says, so there's some questions for you to answer there, and then stop them all. All right, so this is on number 3. Stop all the, now swing a 5th unmatched pendulum. So I'm going to try to swing this guy right here and see what happens. All right, do we see any particular one really swinging a lot or taking its energy? Not really. There's a little bit of oscillating going around, but nothing starting to build in amplitude. And if we did this with sound, of course, we could, if you had a matched frequency of sound, the sound would get louder, because the decibels would get greater, right? Because we said amplitude, like this swinging for sound would be the loudness or decibels. Okay. All right, so that is our first table. All right, so we are at station number 2, singing hose. And it says spin the hose at a slow rate till the hose creates a sound. And then I have the formula that wavelength equals 2 times the length of the pipe. Now, why does wavelength equals 2 times the length of the pipe? What kind of a pipe is this, right? We see 2 open ends. So this is an open end pipe, unlike our last lab where we had one end closed with the water for the speed of sound lab, where that was a 4L formula, right? This is a 2L formula. All right, so I'm going to attempt this and see what we get. So hopefully you can hear some. All right, so that is the first sound that this hose can play. So that's the fundamental frequency of this hose. And we want to know what the wavelength of this sound is, and that means we need to know the length, okay? So I'm going to try to straighten this hose as much as possible. And I'm gonna have to show this to you. Okay, it's not gonna be perfect here. You know what? This is not the best ruler to show either, but okay. So I'm gonna approach the camera here so you can see. Okay, let me line it up real good. All right. There we go. Now you can see where the yellow hose is. I know it's not going to be super perfect because that hose does change size as well. I would say to the nearest centimeter is going to be fine for this. All right, so you're going to have just two significant figures here, okay? And then make sure you change it to meters. Okay, and then if we know velocity equals frequency times wavelength, then we can find the frequency of the sound. All right, next thing says, now spin it faster, at a faster rate till you get the next harmonic, okay? Or the first overtone, okay? That's the first note we had. Uh-oh. Now I know this one did it earlier. It's not as clear, but yes, I think we're getting some bends in it. All right. So here the first note. Okay. All right. So describe the pitch compared to the first sound. What happened to the frequency? What happened to the wavelength there? Okay. And then it says, can you make the hose make the next harmonic? Let's see if I can. And I have a few other hoses to see if we get ones that make it better. All right. So that was the second overtone, or the third harmonic there. So there's the lowest. It does not like that middle one very well, but I can definitely get the third. All right, I do have a few different hoses, and I think they make a little bit different. Oh, that one's not so good. Let's try this guy. If you want to hear. All right, the first guy was the best hose. Okay, so finish your calculations on that one. All right, so at this table, this is the music box, table 3. We have a small little music box. We can see, in case you want to know what the music is, maybe you can see what that was, or you can check that out. So here I will play the music box. All right. Are you having a little bit of trouble hearing it? It's not so loud. All right. So here we have a sounding board. A sounding board could just be a board. This one happens to be in a box shape. And I wonder why we always have our musical player in a box and we call it a music box. I wonder why. Here, I will play this, and now I'm going to set it on top. All right, significantly different, right? So what's going on here? So as this is vibrating, right? Because all it is a set of vibrations is what sound is. Then it is getting this box to vibrate the same. And when you have the greater amount of surface area, it's going to be able to amplify the sound more, okay? So, all right, so that is why a music box is in a box. All right, now we're at table 4, tuning forks. And it says here, provided are 2 tuning forks with the same frequency. So if we look at this, it says 261.6 and 261.6 C. And so they are both here, supposedly the same. However, this one has some tape attached to it. And what is that going to do? It's going to make this one out of tune, okay? So it says strike both the tuning forks and listen carefully. What do you notice happening to the sound intensity? All right, so I'm gonna strike both of these, and we're gonna, I don't know how much you're gonna be able to hear this you know, through the video, but we're gonna hope we can hear this. I'm gonna do it again. Okay. I am not sure if you hear that, and it's really good if we play it, put it near our ears. What we hear is a wah wah thing going on. It's going wah 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 wah, about like that, a little bit slower. We know that as we have these two waves and they're not quite the same, and when they meet, when they both have a peak, if they happen at some point, they're off, but at certain points, they're going to be the same. And when they're same, we get constructive interference and we get an increase in amplitude, or in other words, the intensity of the sound is going to increase. And so it's going to get like loud. Then they're going to be off again for a while because their frequencies are slightly off. And every once in a while, again, they're going to match. And then they're also going to have destructive interference in between. So you get this wobbling of a sound that we call beats, okay? All right, I'm just supposing at this point, because we don't know what this tuning fork actually is playing at now, we just know it's off. But I'm saying here for number 2, if you hear 4 beats a second, what are the possible values for this tuning fork that's got the tape on it? What note is this playing, or what hertz is this playing? If we know this one, right, is 261.6, what is this if we do hear those 4 beats? Okay? All right. Then we are going to go on the other side of the table to part 2. And it says, this one, again, this might be really hard to hear for people at home here. But I have 2 tuning forks. They're both 440 hertz. And so what our goal is, okay, I'm going to strike this one and I'm going to hold it like this to the other one. And remember, if you could actually see it, the tuning forks actually bend, right? And that's what's moving the air and creating a compression and rarefaction. So this tuning fork, imagine, is going to be going. This one has a matched frequency. They're both supposed to be 440. This one has a natural resonance to this one. So when this one is going like this is like the 2 pendulum strings that have matched length. When this one wants to go like this one goes, okay, let me do that too. And what's really interesting is we can go like this. Let me see if I can do it. And I hear this one. I'm going to try to bring this close to my phone there and do it again and see if you can hear it. So we'll set the first one going, okay? I'm going to strike the one, bring it close, stop that one, and then see if we hear this one. All right. Again, you may not be able to hear it. It may not be loud enough. When we place it by our ears are so sensitive. We can kind of pick it up. This one started to hum all by itself. So this one, sending it through the air molecules are compressing and striking this just the right that this thing starts to hum on its own. All right. All right, we are at our final table, number 6. And we have something called talkie tapes. So this is pretty hilarious. I bought these a number of years ago. I heard from another physics teacher, Mr. Callahan, told me about talkie tapes. And then I ended up buying some quite a number of years ago. And now I checked this year and I cannot find, I think they're out of business. What am I going to do now? And so, right. So here is the original information from the company. And talkie tapes, it goes from an idea from Thomas Edison, and kind of like a record player or records, where if you have a record, right, it's just set up a series of bumps that will vibrate. And so, okay, I'm just trying to figure out which is which, but I have 2 different sounds here, or 2 different recordings on this little plastic strip. And how this works is one side has got these little bumps, and we need, so those are going to make vibrations, and how they are spaced will change the frequency of those vibrations. And so there's a little recording in this strip. Now, why do I have this cup on here? Just like the music box without the box is not really a music box. These little talkie tapes, a vibration in this little plastic is nothing. That's kind of like a guitar string just vibrating. So we have this cup here, right, is like our sounding board, and it's going to be our amplifier of the sound. And let's see if you can figure out what this says. Okay. Okay, can you figure it out? Okay, unlike what the one says there, I do not have a happy birthday anymore. It broke from high student use. Okay, I'm not going to tell you what that's saying. All right, then I have my second one. All right, let's see if, okay, you ready? Whoa. What is it? I don't know why I'm not getting this. Okay. I think I have too much rosin on my fingers. Okay, this one's the same. Let's see if this one works a little bit better. I'll tell you what this one says. This one's a hard one to understand. Okay, one more time. You gotta do it at just the right speed. Okay, I'm gonna tell you. This one's supposed to say science is fun. So now listen again. There you go. Okay, the fun kind of gets blurred out there. All right, so those are kind of just fun and interesting. All right, well, that concludes our lab. So hope you had some fun with these things. There's all kinds of things on YouTube with all kinds of other kind of resonance things that you can do, from you know, putting your finger around a wine glass, having just the, you know, making sounds with your voice, or singing really loud with just the right sound to make a wine goblet break, all kinds of fun things. The Tacoma Narrows Bridge, where winds were having a matching frequency to the bridge and making a bridge collapse. The resonance is all around us with sound and other types of vibrations.